Z table has very tiny numbers on it, but it's super important for what we're going to do for a pretty big chunk of the statistics class. You have a Z table now. Soon you're going to get a T table, and then down the road you might get a chi-square table. There's lots of tables in statistics. And the truth is, in the real world, you won't use tables, so it's a little bit funny. Tables are what we use when they're not letting you use a special calculator or a computer program. In the real world, you would just put this into whatever statistical software package is, and it'll spit numbers out like this. But for stats classes, it's kind of classic for them to be like, here's a table. Find the numbers that the computer would otherwise spit out for you. So, show you how to talk about the table, how it works. Usually what happens is people just hand you a table and they show you how to find some numbers on it, but I actually want you to understand what the table's doing because it gets really confusing later if you don't understand how the table works. So I want to explain what the heck the table means. Okay, so first thing, if we're talking about the Z table, we're talking about a normal distribution. And with the normal distribution, we have that classic bell-shaped curve. And a few weeks ago, we talked about the Z-scores. Do you remember when we talked about Z-scores? Okay. Lots of this comes into play with that empirical rule that we also talked about. So I'm going to switch over to a blank sheet of paper, and I'm going to start doing a little bit of a review that's going to help you understand how the table works. If you already understand how the table works, excellent. If you don't, you might be like, OMG, I'm so glad you did this, because otherwise this table seems like really random, that there's a bunch of decimal numbers in here. I want you to know how it works. Because then when we get other tables later, it makes those ones less confusing too. Okay, so first thing, do you remember what the empirical rule told us? We had empirical rule and we had Chebyshev's theorem. The empirical rule was the one where we were required to have basically a normal distribution, at least a bell-shaped distribution. And with the empirical rule, what we said was that within one standard deviation of the mean, so we went ahead and we set that mean right in the middle of the distribution, and we called that z is equal to 0 on there. If we were one standard deviation away in either direction, so if I went out this direction, one standard deviation, that would be z is equal to 1. And if I went backwards one standard deviation, that was z is equal to -1. Do you remember what percent of data falls within one standard deviation of the mean? Ooh, close. This one's 60 something. Do you remember the number? 68% of the data is within one standard deviation of the mean. That's the first thing the empirical rule says. It's approximate. It's not exact. It's approximate. If we went out 2 standard deviations, so if I went out to z is equal to -2, and I went out to z is equal to +2, do you remember how much of the data is within 2 standard deviations of the mean? 95% of the data is within 2 standard deviations of the mean. And then if we went out 3 standard deviations, so that would put us at z is equal to -3 on this side, and z is equal to +3 on this side. Then we've got almost the entire distribution filled in, except for just the tiny tails on either side. That's 99.7% of the data. Is within 3 standard deviations of the mean. And these are all approximate. It's not exactly 68%. It's approximately 68% is within 1 standard deviation. It's approximately 95% is within 2 standard deviations, and approximately 99.7% of the data is within 3 standard deviations of the mean. So if you go out 4 standard deviations, how much do we think we're containing? It's like practically 100%. If you go out 5 standard deviations, it's like definitely 100%, right? So when we're talking about the z-scores are telling us how far away from that mean are we. 1 standard deviation away is not too big of a deal, but once you get out to be 3 or 4 standard deviations away, you've practically got the entire thing. Underneath this curve, these are probabilities. So if I filled in the entire thing is filled in, you'd say 100% chance that something's going to happen. So if I were to give you a picture that looks like this, then. So I've got my bell-shaped distribution, and z is equal to 0 is my mean right down the middle. Then if I shade in this part of the distribution, I shaded in half of it, right? So this should be 50%. If the whole thing's 100%, do you agree that what I just shaded in should be 50%? In terms of a probability, we would say that this was p is equal to 0.5. And so what I want to do is I want to look at our table, and the table has positive z-scores and it has negative z-scores on it. 0 is the one that I'm talking about right now, though. It's neither positive nor negative. We could use either one, but let's go to the positive side just because it's a positive 0 on there. When we look at the 0, it's at the very top for you guys. I know it's super, super tiny. I'll see if I can make it actually big enough for you to see it. Okay. We're talking about z is equal to 0 on my picture. Z is equal to 0, okay? So what we're looking for on the table along the side, see how this is your z column? You're looking for z is equal to 0. There it is, 0.0. And if you come this way across the table, it adds decimals on it if you want. So if we wanted 0.5 for my z-score, I'd come across until I was underneath this part of the column. But if I want it to stay 0, you want to be 0 and the 0, 0. That's just 0, 0, 0, 0. That's definitely 0, right? Totally 0. Look what it tells you the probability is right there. 0.5. Look what we said the probability needed to be. 0.5. So the table is telling us the same thing we already know from the empirical rule. So let's do some trickier ones and let's make sure it's still matching up. Okay, so I'm gonna draw you another picture. And this time, my z is equal to 0, still right down the middle. But I want to go out to z is equal to 1. And I want to know what's the probability that corresponds to z is equal to 1. Probability that corresponds to z is equal to 1, the way the table works is it always starts over on the left-hand side and it fills this direction. So if it's the probability for z is equal to 1, it's all the way from this tail to where z is equal to 1. So it always gets filled in starting from the left-hand side. So when we filled in to the 0, we started over here and we filled into that line. If we're going to z is equal to 1, we started over here and we're filling all the way to the z is equal to 1 line. Okay, so based on the empirical rule, we know that if I'm just talking about from z is equal to -1 up to z is equal to +1, that between here and here is 68%. But if I wanted just half of that region, we had said before that this is 34%. So this piece right here is 34% because 68% would be between z is equal to -1 and z is equal to +1. So if I'm asking you how far is it from this tail filled into z is equal to 1, what I can do is I can take the 50% we just calculated if we go halfway across, and I can add on the 34%. So to go to z is equal to 1, you've got 50% plus 34%, which should come out to be 84%.
You have the 34% registered item 68 by 2.
Because from here to here would be 68, and if I only want that part of it, then I got to cut it in half. Good. So I got 84% using the empirical rule. So that would mean that we had a p is equal to 0.84. Let's use the table now and go to z is equal to 1 on the table. So we need the positive z-score side of the paper. Positive z-score, we're going down to where it says z is equal to 1. So 0.9 is there, 1 is there, and if you come over to the 0, 0, that means this is 1.000, we're right at exactly 1. It's 0.8413. 0.8413 from the table. So remember I said that when we use the empirical rule, it's approximate. We say it's approximately 84% from the empirical rule. If we're using the table, we get a more precise number, but they're hecka close, right? So the table is actually giving you a more precise number than the empirical rule, but the table is doing the exact same thing the empirical rule is doing. But when we do the empirical rule, I only have z is equal to 1, z is equal to 2, and z is equal to 3 when I use the empirical rule, or -1, -2, and -3. But if you look on the table, we can do crazy z's. We can do z is equal to 1.345. We can do other things on the table. So the table lets us be more precise with the z's. So let me do a trickier one. I should zoom out again. Okay, what I just drew is just the tail after the point where z is equal to +2. I want to know what's this area of the shaded part of the graph. So the way the table works, the table tells you everything shaded from here to here. So if I go to z is equal to 2, I'm going to get the wrong answer. Because what it will tell me if I go find z is equal to 2 on the table is it's going to tell me all of this is filled in. Not that part. But what could I do? Compliment. Nicely done. Yes. So if I take 100%, that would be the whole thing filled in. If I take 100% and I subtract off whatever it tells me for z is equal to 2, that's going to tell me what's here. So we would do 1 minus whatever we get for z is equal to 2. So let's look on the table. For z is equal to 2, we're on the positive side again. And for z is equal to 2, it's telling us it's 0.9772. So we need to do 1 minus 0.9772 to figure out what's over in that little tail. So 1 minus 0.9772 gives us 0.0228. There's another way you could have done this. So I'm going to verify we just got the right answer. The other way we could have done this, if I'm talking about areas, the normal distribution is symmetric, which means it's the same on one side as it is on the other, right? So if I wanted to know what's the area from here to here, if I didn't want to take the complement, I could actually do this other trick and I could find out what's the area just up to z is equal to -2, because the area for this tail should be the same as the area for that tail because it's symmetric, right? So what I could do instead is I could go find what z is equal to -2 is, and the way the table works, it tells you everything up to that point. This area should be the same as that area. So let's go look at z is equal to -2. So we got to find the negative side of the page. Z is equal to -2 says 0.0228. 0.0228. So we could do it 2 different ways if we wanted. So either way, we'll end up with 0.0228. So why am I showing you this? I want you to understand that the way that this table is working, it can do 2 different things for us. If we have a z-score, we're looking in this column here, and we're looking across the top to find another decimal on there. So if I wanted it to be -3.5, -3.5, we would say, or sorry, I don't want to do -3.5. I want to do -3.05. Then I would go negative 3.0, and then I would come across to where it says 05 right here. And then I would come down and across and end up with 0.0011. Or if I wanted to do negative 1.98, then I'd come down to negative 1.9 right here, and I'd come across at the top to where 0.08 is, and then you find where those 2 things line up. So I'm too zoomed in to get to the 8 part. Let's see. There we go. So I go negative 1.9, I'd come over to the 8, and then I would see where those 2 things would line up, and I get 0.0239. What that's giving us is areas under the curve. So that's why the picture at the top that she's giving you, it's shaded in from this part starting over on the left-hand side up to the Z line. And it always starts over on the left-hand side and fills from that direction. All these things in the middle of the table are areas or probabilities or percentiles. So all the things in the middle of the table, or I'll write that a little more clearly, all of the 4-digit decimals in the middle of the table not digit, 4-digit. all of the 4-digit decimals in the middle of the Z table are areas under the curve, they're also percentiles, they're also percents or probabilities. That's important because sometimes in the problems you're going to solve, they're going to tell you a percentile and you're going to have to go find the corresponding Z-score. So you'd be using the table backwards. You'd go to the middle of the table and find the percentile, and then you would look across and look up and figure out what Z corresponds to that number. So sometimes they ask you to do the things backwards. I know that doesn't make sense right at this moment. It will when we do some problems. Okay, so using that idea, what is the Z-score that corresponds to the probability P is equal to 0.25? What is the Z-score that corresponds to the probability P is equal to 0.25? Okay, first thing you're doing, you're staring at both of these papers and figuring out where would you find 0.25, not 0.025. It literally has to be 0.25. And it's going to have additional decimals after it because they give us 4 decimal places. So theirs could be 0.2500. Could also not exactly be there, but we would find the 2 numbers it was closest to. And then we do this thing called interpolation to figure out what number we want to use. When I start looking on this side of the table, the numbers are too big. So the positive Z-scores isn't going to be where I'm going to find it. I'm going to find it on the side with the negative Z-scores. Take a second and see if you can find either 0.25 or something really close to 0.25. I found 0.025. That's wrong. I don't want that one, so I got to keep going. So I did not find exactly 0.25 anywhere on here. I'm going to show you where I ended up, and let's see if you ended up in the same place as me. I ended up right down here. I found 0.2514 and I found 0.2483. That was as close as I could get to 0.25. Is that where you ended up? Okay. When that happens, we look in the middle of those 2 numbers and we'll end our thing with a it'll add another 0.005 to the end of it. I'll explain that in just a second. First thing we're doing, we're going to look across this direction to figure out what the Z thing should start with. So when I'm in this row, the Z stem that starts is negative 0.6. So you're going to write down negative 0.6. And then from where we are here, we're going to come straight up with both of those numbers. And up here we have 0.07 and we have 0.08. When that happens, we're going to go with the smaller number and then put a 5 after it. So you're starting with negative 0.675 is what you're going to write because we're going midway between the 7 and the 8. So negative 0.675 is the number we want to write down. And the reason it's the 7.5 is that for this part right here, it's between the 0.07 and 0.08. We took it halfway in between that and we put 0.075. So we're adding that to that part. So let me give you another one. Right. What is the z-score that corresponds to the 95th percentile? So I said this differently than the last problem. I said, what is the z-score that corresponds to the probability p is equal to 0.025? That's the same thing as if I had asked you for the 25th percentile. So if I'm asking you for the 95th percentile, you're looking for p is equal to 0.95 or 0.9500 because there's 4 decimals on this page. You're looking for that. You might not be able to find exactly that. We'll want to find the thing that's the closest to it that we can. This time, the negative z-score page, the decimals, the biggest one they have is 0.4641. That's too small. So I got to go to the positive z-score page to find the 95th percentile. So I'm looking for 0.95 in the middle of this page. And this is actually one of the ones that they use as an example at the bottom. So you'll see a little asterisk if you're in the right location because they're trying to show you something that this is a really common thing for them to ask you to look up. So 0.95, they don't have that on here, but they have 0.9495 and 0.9505. So the z-score we want, we're going to come across here and it starts with a 1.6. So you're going to write 1.6 down. And then from here, we're going to go straight up. And we have 0.04 and we have 0.05. You're going to go right in the middle of those. You're going to put 4.5. So you're going to say 1.645.
So which, I know that you're gonna take the one that's like kind of closest to it, because it obviously wasn't, closest 505. But on the left-hand side, I see that it's 0.9515, and then on the right-hand side, it's 9495. But they're like kind of the same distance away, if I'm correct, right?
Right.
So-
But here's your problem. So I like how you're thinking. If we go between these two numbers, they're both bigger than the number. 0.95, we want one to be bigger and one to be smaller. So this one's smaller and this one's bigger. And so we want right in the middle where one's smaller and one's bigger. Yeah, good. So we're going to write 1.645 as our number. Let's do one more. What is the z-score that corresponds to the 38th percentile? So 38th percentile, you're going to try and find p is equal to 0.3800. It might not be exactly on the table. So if it's not, then you're going to find the two numbers that are closest to that. If you think you found it, is it positive or negative? Negative. Yes, it should be negative. Okay, so 38%, 0.38. Point 0.38 ends up being between these two numbers down here, 0.3821, 0.3783. So I'm coming across, and the thing you're going to write down first is negative 0.3. And then if you go up, it looks like we're either going to put a 0 or a 1. So we got to go 0.5. 0.5. So you're going to write negative 0.305. Another 0, like you want it at the end?
You know, like difference between 0 and 1. Oh wait.
This is weird because, yeah, no, this one's weird because it's 0, 0 or 0.01. And so what you want to do to make it halfway between here and here is make it 0.05. Yeah, I know. It's tricky. That's why I picked that one, because I knew it was tricky. And we're going to end up using it in a problem in just a minute, so we can go back to it. We don't have to go find it again. I'll be like, oh, you guys did this one already, and we'll steal that number. All right, I started with the how the table works part, but let's actually do some problems now so that you care. So far, you're like, this is stupid. Why would I do this? Yeah, I know. But understanding how the table works helps a lot before you get all caught up in the actual problems. So your next page, normal distribution practice problems. A thing we're going to need to do a lot of these problems is the formula for that z-score. It's been a while since we did it. Do you remember what the formula for the z-score is?
X divided by 70.
Beautiful. X minus the mean divided by our standard deviation. Perfect. So, most graduate schools of business require applicants for admission to take the Graduate Management Admissions Council's GMAT exam. This is like the SATs, but for business school, or GREs for grad school, or the MCATs for medical school. Business school has its own crazy test. Scores on the GMAT are roughly normally distributed. Okay, they have to tell us that so that we can do what we're about to do. If we don't know that they're roughly normally distributed, then we can't turn these into z-scores. It doesn't work. But since they said that, we can move ahead. They're roughly normally distributed with a mean of 527 and a standard deviation of 112. What is the probability of an individual scoring above 500 points on this exam? Okay. So in order for us to be able to do this, we've got to convert that score that's not standardized into a z-score. And a z-score then lets us use our normal distribution table to come up with a probability. So we're going to use our z-score formula. The x you're going to use is that 500 here. So my z-score is x minus the mean divided by the standard deviation. We have all three of those things now. So I know it's going to be a negative z-score. Negative 27 divided by 112 gives me a negative 0.241. When we use our table, it only lets us do z-scores to 2 decimal places. So I'm going to write just negative 0.24, but 241 was the next decimal place. So that's why I didn't round it up. Kept it down. Okay. So what we're going to do now is we're going to use that z-score to go find a probability in the middle of the table. So again, the middle of the table tells us probabilities or percentiles or percents. What else did I say it was? I said it was, oh, areas under the curve as well. Okay. So if we want our probability to be that the z is greater than negative 0.24, I want to think about that table. A score above 500, if we think about what that's going to look like in terms of our curves here, our z-score is the negative 0.24. Which means that it's like, oh, I'm doing that wrong. Sorry. I shouldn't have gone that far over. Nope, nope, nope. Okay. Let me put down 0 so that you can see what I'm doing. Here's z is equal to 0. So z is equal to negative 0.24 should maybe be like right here. Okay. What your table is going to tell you is everything below that score. But the question is asking, what's the probability of the individual scoring above 500? So it's asking you for this part. So we're going to get the opposite of what we want. So we have to do 1 minus whatever we go get in the table. Because it's going to give us the score that's below that score. We want the score that's above. So we're going to do 1 minus the probability that z is less than or equal to negative 0.24. And that's going to give us the actual thing we want. So 1 minus, let's go find the probability now. Negative 0.24. So I'm on the negative z-score side. Negative 0.2 is almost at the bottom. And 4 is going to be 0.4052. 0.4052. So we're going to do 1 minus that, and that'll give us what we're actually looking for. Which is 0.5948. So what does that actually mean in terms of this problem? They just said, what's the probability of an individual scoring above 500 on this? The probability is approximately 59.48% of testers score above 500 on the GMAT. Okay, next question's kind of weird. It'll take us just a second to process it. How high must an individual score on the GMAT in order to earn a score in the highest 5%? Okay, here's what we're talking about. Over here is in the highest 5%. So I said that that table tells us percents and stuff. But if I go find 5%, what am I actually going to find? This cute little tail over here. I don't want 5%. If I want the highest 5%, what am I really looking for? 95%. If I want the highest 5%, I need the z-score that corresponds to the probability 0.95. Oops, sorry. I need the z-score that corresponds to P equals 0.95 or 0.9500 if you want to see the 4 decimals that you would normally see. Now, you already did this if you wrote down the stuff that I had you guys do before. You told me the z-score that corresponds to the 95th percentile is z is equal to 1.645. We did this one already. But how do we do that? Again, we were looking in the middle of the page for 0.95, and we found 0.95 was in between these ones. So we came across and we had the 1.6, and then we went up and it was between the 0.04 and the 0.05. So it was 1.645. Now, that's not the answer to the question, because it says, how high must an individual score on the GMAT in order to score on the highest 5%? If you say 1.645, you're saying they need to get 1.645 on a test that we just said most people had like over 500 on. So that can't be right. This is the z-score. We need to turn it back into the x-score. So remember when we did the last problem, we took the 500, that was the x, and we turned it into a z. Right now we have a z, and we need to turn it back into an x. So we got to do some algebra. I promise it's not terrible algebra, but we're going to use that z-score formula. The z-score formula said z is equal to x minus the mean divided by the standard deviation. I want the x by itself now. When you want to rearrange an algebra expression like this, you're allowed to put this z over 1 so that now we've got a fraction is equal to a fraction, and then you're allowed to cross multiply things if you want. There's other ways we could do it, but this is the fastest way. So I put this z over 1 so that you have a fraction is equal to a fraction, and now you're allowed to cross multiply. So if you cross multiply this direction, z times, that's sigma, or the standard deviation. We're going to write z sigma right next to each other. Is equal to, and then now we're going to cross multiply the other direction. 1 times x minus mu is just x minus mu. And I said we're trying to get x by itself. So my last step is to add that mu to both sides. So we're going to add mu to both sides, or the mean. So that cancels on this side. On this side, you have z times the sigma plus the mu is equal to x. Cool. We need the x. So we're going to go ahead and say x is equal to z times the sigma plus the mu. And now we're going to go ahead and just plug those things in. The z-score we got was 1.645. The sigma, we have to go back up to the last problem to get the sigma. The sigma was 112. plus the mu we said was 527. And so when she gives test questions and stuff, that might be where you leave it if you don't have a calculator. But if we have a calculator, and I do, we might as well get the actual score. 1.645 times 112. I don't know. People have told me in the past that they didn't, like, you don't have to use a calculator. You can just put the little star thing next to it instead of finishing the calculation. Okay, so she's changed it. So in the past, people just put a little star when they got to that step. And that's, if you've done this, you did the math right. You just haven't given the final answer. So I was always like, oh, that makes sense. Yeah.
I think combination of both, because she has mentioned that there's, that on the exam we will have to do calculations, and on other times she said that like.
Oh,
You
okay.
might just have us like write up the equation and leave it at that.
Got it. Okay. So it's good for us to know how to do both. As long as you know how to write this part, you definitely know how to finish it if you have a calculator. We're just putting it into the calculator. So I took 1.645 and I multiplied by 112. And then I added 527. And my calculator says 711.24. So we said 59.48% of the testers scored above 500. But this is saying the people who did the really best on this test, the top 5% of people, got over 700. So 711.24 is the top 5% score.
Or is that about the question above?
Yep.
Is it more standard to round the Z-score? Like, if you have another, because you have 0.241, like if that was a 5, would I round it most of the time or not?
Yeah, if it was 0.245, you would round it up. Yeah. Yes. So the reason I rounded it to 2 decimal places is because our table only lets us go out to 2 decimal places on there. But if you wrote 0.241, you just, when you go to look on your table, you're gonna be like, how am I gonna get to 0.1? Oh, I can't, it's just 0.24. But yeah, if it was 0.245, you should round it up to 0.25. Yeah, good question. Okay. We've only done one, I mean, there was a combination of things, but it was only one question so far. So if you're still totally lost, that's really normal. It takes a little bit to understand this. So I don't want you to feel like I should be getting this by now. It takes a few of them to really go, oh, that's what we're doing. Especially because some of these problems go back and forth on what you're looking for. I like the next problem though, because I was like, oh, that's like real world there. The length of human pregnancies from conception to birth approximates a normal distribution with a mean of 266 days. So my mu is 266. And a standard deviation of 16 days. So my sigma is 16. What proportion of all pregnancies will last between 240 and 270 days, which means roughly between 8 and 9 months? Okay. So you actually have 2 X values here, and I'm going to write down one of them. I'm going to say X1 is equal to 240. And I'm going to say X2 is equal to 270. And what we're going to do is we're going to go find 2 different Z scores. We're going to find a Z score for each of those X values. Here's why I think this is an interesting question. When I was growing up, people told me that you're pregnant for 9 months. Well, pregnant ladies will tell you, it can be closer to 10 months, and some are much shorter. So this is an interesting question. What proportion population of all pregnancies are between 8 and 9 months. And then from there, we can extrapolate more than 9 months. So what we're going to do, we're going to find a Z1 using the X1 here. So we're going to say the 240 minus the mean of 266 divided by the standard deviation of 16. And then we're going to find a Z2 using the 270 minus the 266 divided by 16. So calculator. I got negative 1.625. So I'm going to say negative 1.63 for the first one. And then for the second one, I got exactly 0.25. And so what we're asking for is the probability that Z is greater than negative 1.63, but Z is less than 0.25. And so how we do that is we go ahead and we find the probability of the bigger Z. And then we subtract the probability of the smaller Z. And when I say the bigger Z, if one of them is positive and one of them is negative, the bigger one is the one that's positive and the negative one is the one that is the smaller one. So we're going to find the probability of the bigger one. So I'm going to write this out as like a separate step. The probability that Z is less than 0.25 is the thing we're going to find first. And then we're going to subtract the probability that Z is greater than 1.7 or 1.63. So we actually have to go less than on this one. And the reason we have to go less than, even though I know the other direction I said greater than, is that the tables only ever give you less than. The table always fills from the left-hand side up to here. So what we do is we take the probability of the bigger one and we just subtract the probability of the smaller one. There's not really anything, like if you don't write these lines, she don't care. That's not a thing you have to do. I'm just writing it so that you know what I'm doing. What am I actually doing? We're just going to go find the probability of that number and the probability of that number. That's all you're doing. So probability of 0.25. That was one of the ones I already asked you guys to do. You helped me find the probability of 0.25. It was negative 0.675. Oh, nope. Sorry, I'm doing that backwards. That was the Z-score. Jen. Sorry. Don't listen to me. We're going to do that backwards. Okay. We have the Z-score. We got to go find the probability. It's good I made that mistake though, so that now you're like, okay, even Jen gets confused sometimes. These are Z's. Okay. Z is 0.25. That's positive, so we need the positive paper. 0.25 in terms of the Z, 0.2 is here, and we got to come across until we hit 5. Okay. 0.5987 is the number I'm going to write down. Okay. Now we're going to write down Z, we need negative 1.63. So I need the other paper. Negative 1.6 is right here. And then we got to go across to 3. 0.0516. 0.0516. Cool. All right, so now we're just subtracting those two numbers. 0.5987 minus 0.0516 is 0.5471. Okay, what does that mean? So the question said, what proportion of all pregnancies will last between 240 and 270 days? So what we just got is that approximately 54.71% of all pregnancies last between 8 and 9 months. Only 54% of pregnancies last between 8 and 9 months. So that means that there's a really good chance your pregnancy lasts longer than that. So that's why a lot of pregnant ladies are like, don't say it's 9 months, man. It's closer to 10 months. Question.
Where did you put 0.516? How did you find that?
0.0516. So I was looking for the point. Oh, sorry, I didn't put a negative on there. That was probably why you were confused. Pop a negative on there. That might help. Negative 1 point. So we're looking for negative 1.63. So sorry, in the row above, I had the negative on there and I just dropped it when I wrote it in the second row. So negative 1.63. So we're going to negative 1.6. And then we're going to cross to be underneath the decimal of the 03. That's where the 0.0516. Sorry. Yes, if you use the positive, it gives you a very different number, huh? Jen. Yes, call me out on that. I make tiny mistakes like that all the time. As you can see, there's a lot of moving parts to these problems, so it's very easy to make tiny errors. So if you haven't yet, I really recommend you make a homework friend, because the homework problems can be super frustrating if you do like what I just did. And you're like, I don't understand this at all. And the truth is you totally understand it. It was just like a negative sign. And you're like, oh, if you have someone to do homework with, it feels way less scary. Do you know anybody's name in your statistics class yet? Okay, I'm gonna be real lame. Take 3 minutes and turn to some people near you and introduce yourself and say what your major is. Ready, set, go. Hi, I'm. You can yell sideways.
I started studying for the exams.
Yeah, I'm not a big math guy. I didn't realize it was next Friday.
I know, right?
Jeez, I thought we just had it. It's like 3 of them.
Yeah, if you have another one. My friend, like, second one, and the finals just absolutely just hard.
Really?
Open on. I'll drop those in.
Yeah.
Damn.
Two. I was like, sorry, you back. I was like,
Okay, that's it. Stop having fun. All right. I want to make sure that you leave here knowing somebody. And so I'll probably try over the next few classes to have you do it a few times so you have a chance to like catch up and say a few things. And then if you end up taking a friend with you, all the better. But definitely my advice, if you have to take any other math or science classes at UC Davis, all classes is probably a good idea, but any math or science classes for sure, having a friend makes it so much better. And by friend, I do not mean a person that you are gonna hold on to and go hang out and do crazy social things with. When I was here, I had math friends. And the math friends were literally just the people I did my math homework with because I needed help. Just so that I wouldn't lose my mind. Because half the time you're doing the problems and you're like, shoot, is this how you started? Why did you start this? Or you get halfway through a problem and like you know that if you keep going and you're wrong, you're gonna do a whole bunch more wrong work, and it'd be great to be able to just ask somebody right at that point, hey, did you get this before I move forward? Okay, cool, and now I'll move forward. It was great to have somebody to do that with. These weren't necessarily people I did anything else with. We just did homework together, but it was great. It was nice to not be alone for that. I really recommend it. When I was in high school, that wasn't a thing I needed to do. So I didn't realize when I got to college, like the first thing that like successful students are not going it alone. Like really? I thought I was doing something wrong if I needed other people to get through classes. Nope, not at all. Successful students need other people. It's totally normal to need a study group in order to get through some of this stuff. Okay, so here's our next problem. The next one says, what length of time marks the shortest 70% of all pregnancies? So what we're looking for is a length of time right here on the graph. I want to know what number would go there. When we make these normal distributions, it's a z-score. So I'm going to get a z-score first, but then I'm going to need to turn it into an x because that's the actual length of time. The z is just our converted length of time, right? So what I drew is I filled in 70%. That's what I figured 70% looks like. It's probably not perfect, but I figured this is what 70% of this chart looks like. So 70% is 0.7000 if we were to look on the table. So I'm looking for what z-score goes with 0.7000. 0.7 is probably not perfectly on there. Nope, it's not perfect, but I see 0.6985 and then 0.7019. So in between those numbers. So the z-score, we're going to come across this way. That's 0.5 is what we're going to start with. And then we want to go in between the 2 and the 3. So I'm going to say 0.525. 0.525. That okay? That's not the answer to the question. If I say what time and you say 0.525, people will go, what? We're talking about days in the problem. So I need to turn that z-score back into an x-score. We already did that whole algebra calculation, so you don't need to do the algebra all over again. We're going to come back up to where we wrote down that x is equal to z times the standard deviation plus the mean. Okay, so our z-score is 0.525. We're going to multiply that times our standard deviation. We said the standard deviation was 16 days. And we're going to add that on to the mean we said was 266 days. Okay, so we have 0.525 times 16 plus 266 I got 274.4 days. So that means that 30% of pregnancies are more than 274.4 days. So 70% of them are this number or below, 30% of them are more than that, longer. So my additional problems here are essentially the same as what we just did. So if you know how to do the front ones, you can do the ones on the back, but let's at least start this one. I don't think I'll finish all three of them before we have to go, but it's okay. I will post the solutions so you can check stuff later. Let's look at the first one. The average number of acres burned by forest and range fires in a large New Mexico county is 4,300 acres per year, with a standard deviation of 750 acres. So the average, our mean, is 4,300. And the standard deviation was 750. The distribution of the number of acres burned is a normal distribution. What is the probability that between 2,500 and 4,200 acres will be burned in any given year? So this is just like the pregnancy problem where we have two different X values. So I'm going to write down X1 is 2,500 and X2 is 4,200. And that means you're going to go find two different Z-scores again. Sorry, Z. Need to put the X first. 2,500 minus 4,300 divided by 750. And then my second Z-score will come from 4,200 minus 4,300 divided by that 750. So I got negative 2.40 for the first Z-score. And negative 0.13 if I round it for the second Z-score. The truth is you don't have to write out the scary P of Z and less than and all that other stuff, as long as you just know that what we just found are Z scores and you need to go find corresponding P scores for those ones. So what I'm going to write here is just an arrow, and we're going to put P is equal to, we're going to go find the probability for that, and then I'll put an arrow and we'll say P is equal to, and we'll find the probability for that one. And then all you have to do is take the bigger P that you get and subtract the smaller P. So you don't have to do all the other notation if that feels scary. It's actually not that bad. So we're going to go find the Z negative 2.40. So I'm on the negative Z page, negative 2.4. And then 0 just means I'm going to the first column. So negative 2.40 is 0.0082. All right. And then the other one is also a negative Z. So negative 0.13. negative 0.1, and then we got to come over to 3. So we're down here at the bottom, negative 0.13 is 0.4483. 0.4483. So this one's obviously the bigger one, and this one's the smaller one. So we're gonna do the bigger one minus the smaller one. Comes out to 0.4401. So that means the probability between 2,500 and 4,200 acres will burn is 44.01%. Yeah.
So when you're, when you get your, p-values, do you always subtract the, what is it?
Bigger-
X2 versus, or excuse me, the Z-score 2 subtracted.
You're
plus-
always going to take the bigger one minus the smaller one.
I see.
Yeah, bigger minus smaller. Okay. The next one you actually did the hard work for already because I already had you tell me what Z-score corresponds to the 38th percentile. That was one of the things I asked you to find. So it says what number of burnt acres corresponds to the 38th percentile. That means we need the Z-score for that. And you told me the Z-score for the 38th percentile was negative 0.305. So we found that previously. Cool. That's not the answer to the question because that's not acres. So what we got to do is use that formula for we have X as the thing we've already solved for. So we want the X is equal to the Z times the sigma plus the mu. Okay. So we just got the Z. Negative 0.305. The sigma for this one is 750. And we're adding on the mu, which is 4,300. I got 40,000. Oh no, not 40,000. Sorry, 4,071 acre, 0.25 acres. There we go. 4,071.25 acres corresponds to the 38th percentile. I'll post the answer to the last one. I'll set you free. I won't make you suffer through another one, but then this way you have something you can practice and see if you've got it. I'll post the answer in Canvas so you'll have something to look at. Thanks for hanging in there. I know there were lots of calculations today. The sign-in sheet is, I believe. Actually, I don't know where the sign-in sheet is.
It's okay, sorry, I get started.
Perfect. All right, send the sheets up here if you didn't get it.
But 38.
Yeah.
I think.
Oh, I see.